Hello everyone. I welcome you all to my new video. In this video, I'm going to discuss uh, one of the fundamental in civil and mechanical engineering. This video helps especially the undergraduate students then who are studying mechanical or civil engineering. So they also can develop uh, damage model. So by understanding this video. In this video, uh, I'm not going to discuss many mathematical derivations rather than uh, discussing most of the equation and everything. So let me give some idea then how you can think when you model uh, uh, damage or cracking in the material. For in this case, I'm going to use the reinforced concrete beams. Okay, so before going into this video, let's understand the stress. Uh, you might have studied in your strength of mechanics or mechanics of material class, the stress is a tensor. Okay. Also, you studied you have 9 components in that stress, right? So let me explain why do we need 9 components. So this is one of the important questions, right? So you might you might not have properly uh, given the exposure. What is the theory behind these 9 components, right? Also, most of the books you don't get enough information to understand these questions, right? So let me explain you how I understood this one, right? Let's take a one plan. This is the plan. Then we have 3 axes, right? So I use R red color for the x-axis, green color for the y-axis, then blue for the z-axis, RGB, right? The same color code I followed ETUBs and SEP 2000 they use, right? So let's take one force or stress component, right? Let's take the force acting on this flat. Then how can we explain this force? Because this is the arbitrary directions. So our coordinate systems I have represented here. Therefore, I have to decompose this force along these my coordinate systems. Then, if I decompose the force, if I divide by area of this the point, the infinitesimal element, then I can get the stress, right? So let me decompose this force. One, the vertical, that means perpendicular to this plan. This actually parallel to my z-axis. Therefore, if I convert this one into the area, that divided by the area and convert into the stress, then I will get my sigma z components, right? Similarly, now the same the force now the vertical direction, right? So I can decompose into the horizontal, that means along the plan directions. But these directions not parallel to my horizontal axis, right? So just I exaggerated that arrow to make you understand better, right? In this case, I have 2 axes, but again, this force is arbitrary along that plan. So now this component I can decompose along the x-axis. So that will be my tau xy, that means here zx. Okay. Then similarly, if you decompose into y direction, that will be my tau zy. So you know the first letter subscript represent the normal direction of this particular plan. In this case, my normal direction is z-axis. That is what all the first subscript start with z. Okay. So this is now I have considered only one plan. But in the general case, the force can be arbitrary, right? If I consider the most general case, that means force passing through my this corner of my infinitesimal element, then that force can be decomposed along these the three plan. In this corner, if you consider the cube corner, you have three plan on that corner, right? So for example, let's say this is my the cube. If I have the force and this direction, this force I can decompose one, two, three plan, right? I can decompose into three perpendicular direction, right? So therefore, each plan I will end up with three components, like I explained in previous case. For three plan, I will end up with nine components, right? So that is what you have, nine components in the stress tensor, right? Okay. Then let me move on to the principal stresses. What is principal stress? Okay. You might have studied the principal stress something uh, the stress act on the plan where the shear stresses are zero, right? Why that definitions, right? Why we define that way? That is what I am going to explain here, right? This is something you have not discussed in your classes, right? I am giving some additional information, right? Let's take our previous examples, right? We have three coordinate axes, then we have the force. The previously what I did, I decomposed this force parallel to each axis and convert into the stress. So now what I can do, rather than decompose the force, I can rotate my plan perpendicular to my given force, right? So in this case, this is my force. I can directly convert as a stress. This force, parallel to my z-axis. Here, there is no x and y component, right? Actually, my shear stress is zero. This is my principal stress, right? You understood from this approach, in both cases, I just transfer the force according to my orientation, right? In the first case, I decompose the force. The second case, I rotate the plan, right? Both are same. What is principal stress? Actually, that is the actual stress inside the material, right? Inside the element. So that means, in other words, that is the resultant. Principal stress mean, because you studies many things, right? More circle and everything. Why do we develop the more circle and everything? To find the resultant stress of that nine components, right? It is actually the resultant. Okay. So this is something you must understand, right? Okay. Then this is the resultant. What is this? This is the principal plan. This is one of the important point, the one I have noted here. If this principal stress, if it is a tensile stress, if this major principal stress, the corresponding plan would be our cracking at the failure, right? So that would be the crack orientation. Okay. So this, I hope this small explanation uh, would give you a lot of confusion was in your mind. Why do we need to study this much of the complex motorcycle and then stress tensor and everything, right? Okay, let me move further, right? So, as I told earlier, this is not something like your traditional session, right? So here I am giving some bit of interesting and advanced topic, right? How you can think, but not, yeah, I cannot say advanced. How you can think the so far you have studied some theories, right? How you can apply those theory into real life application, right? So now let's take the concrete beam, right? 4 point loading. That why I call 4 point. Here I have two support here. So one support here, then another support here. Then there are two load here, right? So altogether 4 point. When you apply the load at the file here, so you can see these are my crack pattern, right? As I told earlier, if I calculate the major principal axis direction, the perpendicular to that major principal axis, that means this is my major principal stress, the perpendicular to that stress, it will be my principal plan. That principal plan actually the crack orientation, right? So that means if I calculate the principal plan, principal stress in each point on the beam, the perpendicular to that point would be my crack orientation, right? So you might have studied from your simple bending theory in the beam, this is the normal stress distribution. The shear stress distribution is a parabolic distribution, right? If you take this fiber, right? So top or bottom, let's take the bottom fiber, right? Because you have the tension at the bottom. If you take the bottom fiber, you see the shear stress is zero, normal stress is there. Then what is that stress actually? That would be your major principal stress. In this case, it is a tension, right? So therefore, the perpendicular, this, how the normal stress will act, it will act this way, right? The normal stress will act in this way, right? Horizontal direction, right? Okay, normal stress act this way. So that means perpendicular to this normal stress would be your crack orientation, right? That's what you see. The crack here is a vertical, right? When you move towards to the neutral axis, you will have shear stress here, right? So therefore, your the principal plan orientation will not be vertical because you have the shear stress here, because that is not the principal stress. Therefore, you remember the Mohr cycle, you have to rotate the plan, right? Okay, so that means the crack orientation would be different, right? When you move away from the bottom fiber, right? Okay, so this is something you must understand, right? So what I'm going to do here now, let me apply the things so far we discussed, right? So let me take the examples, right? The following example. Let's consider the 10-meter beam. We have distributed load here. Beam width is b meter, depth is d meter, right? Then you know this is from your simple bending theory and this is from your Mohr cycle, right? For simple bending theory, you know the normal stress and shear stress equations. Then this is from my Mohr cycle, right? From the Mohr cycle, the principal plan. So this is the equations, right? So very important point is my x and my shear normal stress, shear stress and principal planes all are function of x and y. Why x and y? Because my bending moment is vary each point. Shear stress also different. Okay, you know, you remember the shear stress. Support is the maximum, close to the center is zero. The bending moment, because I am going to take the simply support, the mid span, you will get the maximum value, right? So that means at the end you will get the normal stress and shear stress at the function of x and y. Similarly, at the end you will get the principal plan also function of x and y. So what I have done here, I use Python to understand, to model this equation to get this simulation, right? Um, So here I use Python. Even you can use Excel, but the problem is Excel giving these animations. You can give. You can use Visual Basic. Then, if someone familiar in Visual Basic, you can develop this one. But here, because I am I'm much familiar in Pythons, therefore I use Python here, right? So let's first we define the beam, right? Okay. So let me take the beam depth close to 500, right? Uh, okay. So I'll take some large depth, right? I can explain better, right? I'll take the maximum depth. This is the depth of the beam, in this case 2.5 meter, but this is just for the illustration purpose, right? Okay. Then the beam width, let me take it is around 0.5 meter is the beam width. So you won't see the corresponding view, the width view, because it's a two dimension. When I increase B, you can see this value here, the principal stress value will change, right? Because when I change the B, the shear stress will vary, therefore principal stress vary, right? Okay. Then also let me increase the load. Let's see, around 50 kilonewton per meter, right? Okay. Here you see something. This is actually the crack orientation, right? The red arrow, the crack. Okay. So something I have to show you, the major principal axis, right? So you can see the gray one is the principal axis, major principal axis direction, the major principal stress direction, right? If the major principal stress in this way, the perpendicular to that stress, okay, perpendicular to that stress, okay, let me bring the spotlight. Okay, principal stress in this direction, the perpendicular to that principal stress, my crack orientation, right? Here you see, then all the cases, the crack orientations is perpendicular to the principal stress. You see here, close the midpoint, the bottom fiber, the crack orientation is vertical. Why? Because I have shear stress is zero, right? Exactly at the midspan, because shear force is zero, shear stress always zero, the parabolic shape, right? When you move close to the neutral axis, the orientation is changed, right? Orientation is not vertical, right? So let me unclick this one. Okay, so let me increase the number of points. Then x point that means along this direction, the how many point I have taken now, so far 15 point, right? If I increase this x direction point, that means I can get closer and closer, right? Let me increase the point here. Then if I increase the number of depth point, okay, higher, you see, ultimately I can get the crack profile of the beam, right? Here I didn't use any complex theory, right? So this is just the basic what you have studied. From that basic, I explain how can you capture the crack profile mathematically in your beam section, right? So if I increase the number of point, finally I will get the crack, complete crack profile of the beam, right? This is actually the crack, how the crack will develop along the beam, right? Okay, so it is interesting, right? Uh, Uh, so let me stop at this point, right? If you have any doubts or if you need any further explanation, let me know in the comment sections. Also, like, subscribe, and share among your students group. Then your support's kind of a motivation to my channel, right? Okay, so see you in next video. Thank you very much.